Hi guys, welcome back. Today we'll look into yet another dynamic programming problem called the minimum jumps to reach end of array. Okay, let's look at the problem with an example. You are given with an array of integers, and the problem is you need to find the minimum number of jumps to reach the end of the array. Okay, what is minimum number of jumps? We start with the first element, let us say this number 1, and we can jump from one element to another element by taking maximum number of steps that is equal to the array element. So here what I mean is, we can, in the jump that we can take, we can only go one step. Okay, so this is the only choice we have. When we are at the second element, the next jump we can either jump by 3 steps, maximum 3 steps, minimum any 0, 1, 1 or 2 or 3 steps. Okay, so this is the minimum jumps to reach end of array problem. So the goal is you should find the minimum number of jumps to reach the last element in the array. So as you can already see, there is at every element that we consider, there are three possible paths here in this example. If we go from 5 and then take a jump, then we'll be able to take one set of paths. If we reach 8 and then continue, we'll be able to go to some other elements. Like this, for every element we have a choice. Okay, and again here, like other dynamic programming problems we have seen, here also for every element that we consider, we have a choice to take, and we explore all the paths in the brute force approach and try to go on optimizing it either through top down memoization, or we will solve it from a bottom up approach where we will first find the solution to the smallest problem and then go on finding the solution to by considering more and more elements in the array. Okay, today let's look at all the approaches. We will be starting with top down approach with which will have exponential time complexity, and then we'll move on to looking at how we can optimize it into quadrilateral or big O of n square time complexity solution. And then in the next part we'll look into how we can still bring down the time complexity to big O of n. Okay, anyway, let's start with the top down approach. In the top down approach, we kind of divide the given problem into small sub problems, and then using the solutions to sub problem, we try to find the solution to our given problem. Okay, so here also let's start by looking at the first element. Okay, so let's look at the first element. Let's call our function. This solves the problem. Okay, so here we have an example here. We have 11 elements. These are the elements, and the output should be 3, because from 1 we can go to 3, and from 3 we can go to the fifth element, which is 9, and from 9 we can go till the last element. So it takes 3 steps. Okay, so here let's store the number of steps that we can take from the current position in the steps variable. So here an important step is to identify the subproblems. Okay, so at every point in this function we will be considering the item at position I. So considering, let's say our I is at position 1, that is looking at 3, then we have 3 choices to take. Either we can go to step 5 or 8 or to 9. Okay, maximum 3 steps. So we explore all the 3 choices. That means we first here, since we are dividing the given problem into sub problems, first we find the total number of minimum steps required to reach 5 and minimum number of steps to reach end of array from 8, minimum steps number of steps to reach end of array from 9. So once we find a solution from all these elements, we know that we can reach these 3 elements in one jump from 3. Okay, so this is the identification of small subproblems. So we take all the 3 steps and explore all the 3 paths. Okay, so from first taking one step to taking all the steps. we need to find the minimum number of steps from all the elements we can reach. Okay, so let's have a variable for tracking minimum, min value. Let's initialize it to maximum. We are finding the minimum number of steps to reach end of array from 5, 6 and 7. Okay, so by taking all the possible steps we explore those solutions. These are all constants, array and n. Okay, so we need to take minimum. So minimum value is minimum of the current minimum and the value that we get from by solving. Okay, once we get the minimum number of steps to reach 5, 8 or 9, I am considering this with an example that our current I points to 3. Okay, so we return minimum value plus 1 because from 3 we are taking one more jump. Okay, so this the result of this function is the number of jumps that we are returning. Okay, now we still need to add the base condition. The base condition would be when we have looked at all possible items. So one of the base condition is if our I goes greater than or equal to n, we just return. Since we are returning a minimum value, when our I goes beyond n, we return an invalid condition. So we return maximum. We can also return -1 as the problem says, and check the condition here inside. If it's -1, we won't consider that into minimum value, but since we are taking minimum, let's keep the invalid condition as maximum. This is the invalid condition. Now the valid condition would be when we reach the last element. When we reach the last element, we don't have any further steps to take, further jumps are not needed. So the number of jumps to reach end of array when we are at the end of array is just 0. Okay, so let's run this solution. As you can see, we got an output of 3, the expected output. Here are some modifications that you can do is here, along with taking the minimum value, you can keep track of minimum index. Okay, so you know from where to which actual index you are taking the jump to. So that can help you to track the exact path you are taking. The time complexity in this brute force approach would be, let's say we have our largest element in the array is k. So this is the worst case. When we have largest element, we can take the maximum number of steps. So that means maximum number of recursive calls, more number of recursive calls to the upcoming element. So this will continue till n. Okay, so if you imagine a recursive tree, our node can have maximum of k branches, where k is the maximum largest element in the array, and this can continue till n levels. Okay, so this is a really huge time complexity. It's exponential time, that is k power n. We can memorize this solution and bring down the time complexity to big O of n square by memoizing. So here, instead of directly returning the result, let's store the result in memory. So our input in the recursion, the only parameter that's varying is I. And since we have overlapping subproblems here, memoizing it like this will help us with reducing time. Okay, in case if you are not clear with this concept, you can see my Fibonacci sequence and knapsack problem videos, where I have completely in detail explained how dividing it into subproblems and how memoization affects in perfect detail. So you can look into that. Okay, anyway, continuing with this, now if my output for the given input I is already in the memory, I just return that, and yes, we need to return that. And if it's greater than 0, then that means it's already cached, so we return and we get the same output. Okay, so this is the top-down approach. Alright, in the next part of the video, let's get into the bottom-up approach, where we get the reduce the time complexity to big O of n square and also look at a solution which gives us big O of n time solution, which takes only constant space, no extra array required. So let's look into the solutions in the next part of the video. Okay, so the link is given in the description. Hope you guys understood this approach. If you did, please like, share, and don't forget to subscribe. See you guys next time.